These are probability notes 5 combinations. Today we're going to distinguish between permutations and combinations. We're also going to calculate combinations. We've talked about permutations in class. They're arrangements of items from a set where order matters. If we have 4 people, Al, B, Carl, and Deb, running for president and vice president, there are 4 P2, or 4 times 3 equals 12, different arrangements of a different president and vice president, where the president's listed first. A, B is a possible arrangement where Al is president and B is vice president. See if you can list the other 11 two-letter permutations using A, B, C, D. Pause the video and we'll return in just a minute. So you can see that we have 12 different combinations possible. Again, order matters. That means that when we write down AB, that's different from writing down BA. Combinations, on the other hand, are the number of ways of choosing items from a set, and order doesn't matter. If we choose 2 people from Al, B, Carl, and Deb to attend a conference, there are 6 ways to choose these people. Here, AB means the same thing as BA. In both cases, Al and B are chosen, so we only need to include one of these combinations. AB is a combination, and there are 6 altogether. See if you can come up with these 6. Pause the video, and we'll be right back. I wrote down AB, AC, AD, BC, BD, and CD. They are some of the same arrangements that we had earlier with our permutations, but you'll notice there are some items like BA that I'm not going to write again because I've already written down AB, or things like CA because AC's been written already, or CB, or DA, or DB, or DC. I'm not including any of these because some ordering of the letters already appears here. And we said order doesn't matter, so as long as we list them in some order once, that's good enough. To calculate combinations, to know that there were 6 ways to choose these people, there is a formula. NCR represents the number of ways that R items can be chosen from N items, and the C means combinations. It also means the word choose. There's a formula down here which should look kind of familiar. It should resemble the formula that we used for permutations the other day. The only difference is that there's this R factorial in the denominator. So to verify that there are 6 different 2-letter combinations of A, B, C, D, let's substitute 6 in for N, 2 in for R, and solve this out. Pause the video, and we'll see what you come up with. So I copied the formula here. I'm using 4 for N and 2 for R. So in my formula, I'm going to have 4 factorial in the numerator. The difference, 4 minus 2 factorial in the denominator, times another 2 factorial down here. So you can simplify this a bit here. We have 4 factorial up here, and we have 2 factorial times 2 factorial. Now if you want to crunch this out, you can do 4 times 3 times 2 times 1 on the top, 2 times 1 times 2 times 1 on the bottom, and when you crunch this out, you'll end up with 24 over 4, which equals 6. If you want to use a calculator shortcut, by all means you can do that as well. The calculator command here that we would use is 4NCR2. You can type in the 4 button on your calculator, hit math, go over to probability. You're going to see the NCR command. Then you can choose 2, hit enter, and you'll get 6. What I'd like you to do is I'd like you to go on and see if you can solve problems 1 and 2 in the worksheet. We'll pause the video and see what you get in just a minute. In problem 1, we've got 47 lottery numbers. We want to choose 6 of them. So we're going to do 47, choose 6. We use our numbers in our formula. Eventually we get 47 factorial over 41 factorial times 6 factorial. You could type that in your calculator. You could type this in your calculator. You could type this in your calculator using the NCR command. In any case, you end up with 10,787,573. If you bought a ticket for every single possible combination, it would cost you, obviously, over $10 million. For number 2, we want to choose 4 of our 10 friends. So we have 10 friends. We're going to choose 4 of them, use our formula, and you get 210. Now, let's say out of these 4 friends, there are 2 that you specifically want to invite. So we're going to look at a case where we want to invite Bart and Lisa. We're going to choose 4, but Bart and Lisa are going to be 2 of those 4. So what we're going to do is, out of these 2, out of Bart and Lisa, we want to choose both of them. And then out of the remaining 8 friends who are left, we have 4 friends we can choose altogether. We've already chosen 2, so out of the 8 remaining friends, we're going to choose 2. So out of Bart and Lisa, these 2, we're going to choose both. And out of the 8 remaining friends, we're going to choose these 2. And if you crunch this out, you can actually type this in your calculator, and you'll get 28. Verify this on your calculator, and then try to solve problems 4A through D. Pause the video, and we'll be right back. So in part A, if we're choosing one letter out of 4, we would do 4C1. You can work out the formula, you would get 4, and that just means it'd be one of each of these letters. If you're choosing 2-letter combinations, 4 choose 2, we know that's equal to 6, and examples would be like MA, MT, MH, AT, AH, and TH. If you put HT instead of TH, that's fine. You remember, just list it once. For 3-letter combinations, we do 4 choose 3. What's interesting is when you get to the third kind of step, like if you compare this with this, it's the same fraction. So you should get 4 here. You can see the 3-letter combinations. And for choosing 4 letters, if you do 4C4, you actually get 1, and the one way you choose 4 letters is to choose the 4 letters. One interesting point is there's this 0 factorial in the denominator, and surprisingly, 0 factorial is always equal to 1. It's not equal to 0, it is equal to 1. So basically, that's where you get the 1 from. In problem 5, you've got a question dealing with poker. See if you can solve this out, and we'll come back and look at your answer. Pause the video. We'll be right back. So in a game of poker, you're dealt 5 cards from a deck of 52. That's 52 cards, and we're choosing 5 of them. You can work out the formulas. If you want to do 52, choose 5 on your calculator. You can do that. Answer you get is 2,598,960 different possible poker hands. Now in 6, we're going to look at a specific hand. The probability of being dealt a flush of all hearts. There are 13 hearts in a deck of cards, so out of the 52 cards, 13 of them are hearts. It's a probability question, so our sample space, the total number of hands possible, is what's going to go in the denominator. You can call that 52 choose 5. The numerator is the specific event of being dealt a flush. Now we know that there are 13 hearts. Of those 13, we're going to choose 5. So how many different heart hands are there of all hearts? Well, we're going to choose 5 out of the 13 hearts in the deck, and we're going to put out of the possible number of hands altogether. Now 13 choose 5 is equal to 1,287. We already know what 52 choose 5 is. That's 2,598,960. When you divide these numbers, you get approximately 0.0005, which is basically akin to getting a flush of all hearts in a hand, 1 out of every 2,000 hands. Pretty unlikely. Again, where do the numbers come from? 52 choose 5 is your sample space. In the numerator, we want 5 hearts. There are 13 hearts to choose from, and we're choosing 5. So for number 7 in a game of poker, what's the probability of being dealt a flush of any suit? Hearts, diamonds, spades, or clubs? Well, we're using the term OR here, which basically means addition. So you can basically add this 0.0005 number 4 times. Or another way of looking at it is take 1287 over 25,98960. I guess I could have called that 2,598,960. And we're just going to multiply this by 4. And when you crunch this out, what you get is approximately 0.0019, which still is a pretty unlikely event. It's basically 0.002. This is 2 tenths, hundredths, thousandths, 2 out of 1,000, which is approximately, or not approximately, basically equal to 1 out of 500. So that's a little bit better likelihood than what we had here. And that's how you handle combinations.